first, let us complete the solution for the linear recurrence relation of the, let me repeat the whole name of this equation. Second order linear homogeneous recurrence relation. That's the full name. Yeah. What do we have so far? We have two non-integer solutions. Our goal, we want to combine two non-integer solutions to get one integer solution that satisfies the initial condition. Yeah. To do that, the key is the combination. In what way? What is the question?
Is it like a linear combination?
Yes, good. The key combination, linear combination. Linear combination. That is the key concept I want to talk about. Linear combination of two variables x and y. Why linear combination? First, we have linear equations. So the structure is linear, the first thing. Okay? Second, it's easy. It's easy, simple, so we do not need to, deal with a lot of complexity. Yeah. This is the linear combination. Two variables, x and y, we want to create a new expression that is the linear combination of those two variables. So with two constant, capital A, capital B. Okay? Yeah. But these two constants, we have freedom to choose those two constants. Yeah. Sometimes freedom is good. Why? If you have freedom to choose capital A, capital B, you can choose appropriate A and B such that the initial condition is satisfied. Yeah. Yeah. That's the reason we need a freedom, capital A and capital B. Okay? All right. Now let us do it. Linearity property. Yeah. So here we need to explore the linear equation. So they have the linearity property. Why the linearity property is good? Think about it. Here, the linearity property is so important here. Yeah. Let me tell you why the linearity property is good here. You have solution 1, then you have solution 2. If you add them together, you get another solution. If you do linear combination, you get another solution. That is the reason the linearity property is useful here. Yeah. All right. Any linear combination of two solutions is also a solution. That is the reason we need that linearity property. Any linear combination of two solutions, x corresponds to the first solution, y corresponds to the second solution. After the combination, linear combination, we get another solution with freedom. Yeah. Because any capital A, any capital B, we get a solution. How about that? Then you can change value of capital A, value of capital B to satisfy initial condition. Right? Yeah. New form of a solution. Capital A plus the first solution, capital B plus the second solution, linear combination. How about that? Yeah. Based on the linearity property, we know this new expression is also a solution there. A solution. Okay? Yeah? Yeah. Look at that. Okay? Now, we have freedom to choose capital A, capital B, targeting initial condition. Okay? So our last step, we fix capital A, capital B. use 2 initial values. Now, let's do that part. All right. Plug in, yeah, because when n equals 0, let us plug in n equals 0 in the formula expression A0. A0, that is F0, that is 0. So capital A plus capital B should be capital 0. Okay? Yeah, so B equals negative A. Let us look at n equals 1, F1, all right? That initial value. Plug in n equals 1, the same expression equals that A1. A1 equals F1, that is 1. Okay? Replace B by negative A minus A, then we take that A out, simplification, the sum of 2 parentheses, root 5, A dot root 5 equals 1, A equals 1 over root 5. Okay? B equals 1 negative 1 over root 5. All right? Then replace A by 1 over root 5, replace B by negative 1 over root 5. Our final solution, we know, yeah, golden ratio, yeah, golden ratio, but the 1 minus, that is negative 1 over golden ratio. Yeah, 1 over golden ratio, negative. Okay? Now, our final expression here, you can see that's exactly our current Fibonacci formula. How about that? So that's, you see, something just like magic, but actually we go through rigorous calculation, derivation, very rigorous derivation. Yeah. Look at the whole procedure, okay? Whole procedure, all right, yeah. So this is a standard way to solve linear second order. Yeah, not higher order. Higher order you can do the similar way, but much harder. Okay? Second order linear recurrence relation in this way. Now, so in homework assignment number 1, you do not have this one, but in test 1 you will have this one. Okay? Oh, test 1, that's the midterm. Midterm. Yeah, I will give you 1 question of that. But in your discrete math, this topic was covered. If you still, you have the notes, so probably you can find the, examples. Yeah. All right, yeah, so we complete whole module 3. Yeah. Next, let us start module 4. Module 4, another very important topic, divide and conquer approach. Divide and conquer. Yeah. That is a big, important topic. Yeah. Let me switch to module 4. Part A now. All right, look at that. Divide and conquer approach. Part A, introduction to divide and conquer and insertion sort. Yeah. 8.1, start with insertion sort. First, let me do some quick introduction to the divide and conquer approach. Yeah. We did some examples, divide and conquer, but here let me just quickly go through that basic procedure using about 10 minutes. Yeah. All right. Decrease and conquer. That is the name used in our textbook. Yeah. But actually, for other places, people do not use that name. Only our textbook, special name in our textbook. A special case of divide and conquer. Yeah. In our textbook, it uses several categories inside divide and conquer. But divide and conquer is a big category. Then inside it, so the author used some smaller categories. Yeah. All right. Yeah. Under a similar situation, yeah, because when we do divide and conquer, we want to consider the original problem for different problem sizes. The problem size is larger, smaller. We can change the problem size. Yeah. But those different problems, we call the subproblems. Yeah, because when you make the problem smaller, we call it a subproblem. Okay? Yeah. They have the similar situation, exploring relationship between a problem and a solution to a subproblem. Yeah. Bridge the gap. Remember this idea, bridge the gap. When you make the problem smaller, suppose you have a solution for it. Because when the problem size becomes smaller, it is easier to solve. Yeah. So you can assume you already have the solution for a problem with smaller sizes. Yeah. But from problem with smaller size, how do you get problem of larger sizes? There is a gap. So you need to bridge the gap. So how to bridge that gap? You need to find the relationship between the current problem solution and subproblem solution. Connect them. That is the key of this method. How to divide? Yeah, when we divide a problem, there are many different ways to do the divide. Actually, we have seen many. Okay, we have seen many. Size 1 reduction. Size 1 reduction. Decrease by a constant. 1 is that constant. Every time we reduce the size by 1, here, not necessarily 1, just by a constant. All right? Decrease by a constant factor. Constant factor, yeah. Remember that binary bits problem. Binary bits problem we did reduce by constant factor 2. Okay, constant factor 2. Yeah. Variable size decrease. Greatest common denominator problem. Variable size decrease. Right? Yeah. Yeah. So although the author of our textbook used 3 different categories, yeah, but for us, typically, we do not need to get into those types. You just understand there are that 3 types. Yeah. But we call them divide and conquer. Yeah. All right. Recursive or non-recursive. Yeah. This topic, actually, I explained when we talk about recursive algorithm before. All right. Yeah. Here, basically, I just want to connect recursive and divide and conquer because they have some close relationship. Yeah. Usually, when we use divide and conquer, it is highly likely we do it recursively. We do it recursively because we need to connect current problem solution, subproblem solution, relationship. That is the recurrence relation. That is exactly the recurrence relation. Okay? Yeah. So here you can see recurrence method, very powerful. Very powerful because that is the typical way using divide and conquer approach in solving problems. Yeah. So that's why when we discussed recursive algorithms, I said we do not try to avoid recursive algorithm because it is very powerful. We don't want to avoid. It is very powerful. Yeah. All right. Yeah. It results in recursive method. Yeah. That kind of relationship you exploit resulting recursive method. Yeah. But this kind of thing, sometimes you can do it, changing from recursively to iteratively. Sometimes you can do that conversion to reduce the resource. Remember, resource reduction. To reduce the resource. But many times you cannot. It's hard. It's hard to make that change. Yeah. So that's why if you can improve in this way, usually for relatively easy questions, relatively easier problem, you can do that change. But typically for pretty complicated problems, you cannot make that kind of change. Yeah. All right. The reason, use less storage space. Yeah. Remember, for the recurrence implementation, we need to use stack inside the memory. Inside the memory, oh yeah, I need to change the color. Yeah. Yeah. All right. Inside the memory, for recursive, we need to use the stack to implement recursive algorithm. And the stack could be very deep. If it is very deep, you use a lot of memory resource. Yeah. So if you can change in this way, you can save storage space. But the problem is, most of the time, you cannot make that change. So you have to use the recursive way for your implementation. All right. Yeah. But when you do the change, usually there are two ways, bottom up and top down. Yeah. Starting from a solution to the smallest instance of the problem. Yeah. What's the bottom up? Yeah. Fibonacci number, you start with F1, F2, that's bottom. Then you find F3, F4, bottom up. Okay? Yeah. Yeah. Top down, you start from f of n. In order to find f of n, you need to find f of n minus 1, f of n minus 2. That's top down. Okay? The bottom up, f1, 2, 3, 4, bottom up. Top down, fn, n minus 1, n minus 2, top down. Okay? All right. So, but the iterative way, we do the bottom up way. Not top down. Top down, recursive, right? Top down, then recursive way. Bottom up, iterative way. Okay? Yeah. All right. Yeah, so that is, yeah, here, let me just give you 2 minutes. So that is our short introduction of divide and conquer. Yeah. Brief introduction. Yeah. Next, in this whole module, we apply divide and conquer to solve several different problems. Yeah. Yeah. Of 3 types, our 3 basic types: sorting, search, sort, and selection. 3 types. Yeah. We use divide and conquer to solve them. Yeah. The first one, insertion sort. From the name, you know, the key operation is the insertion operation. Insert, you know, insert. That operation. Okay? So the same problem we solved before, yeah. But here, this time, we apply a new method, new view of it, strategy. Okay. Start with a simpler case. Again, yeah. So let us try to sort an array with very small size. Then we grow the data size gradually, yeah. And we try to find some rule. Okay? Then we apply that rule, we can generalize our solution. Yeah. All right. Every time we just increase size by 1. Yeah. All right, yeah. The question, how to connect two adjacent cases, n and minus 1, how do you connect them? How do you bridge the gap? Okay, yeah. So let us do some work here, using a diagram to do the work. Use our intuition here. Yeah. When we start the first array, one element array, how about that? One element array, it is already sorted, right? No need to do any comparison, already sorted. All right, so it's done. Yeah. But after that, we have a new element, A1. We want to make, after we add A1 into the current array, we want to make it sorted. Yeah, so it's very easy, right? We do just one comparison, we can sort it, right? After one comparison, we can get it sorted. Now, our current array is a sorted array, A0, A1. It is sorted array. And suppose a new element comes in, A2. This time, we need to put A2 in this array, current array, and make a new sorted array. Okay? So we need to do some work, right? Bridge the gap. There is a gap. After add a new element, you need to do some work. That is the gap. Okay? All right, so when you try to put it in somewhere, right, you don't know which place to put it. Okay? So that operation, is it like an insertion? We insert it in some right position into the array. Okay? Yeah. All right. Add a new element to the current sorted array and make it sorted. Yeah. All right. So that action like insertion operation. All right. Yeah. We'll keep going when we have a current array already sorted. But now we need to add a new element, A sub k, into it. And we need to do one special operation. So that operation, we insert an element in a sorted array at the right position. Okay? We need to find the right position. Then we need to do the insertion. We need to make room for this new element. Okay? Then we arrange the remaining elements to get a sorted array. So that is our idea for this new method. Okay. So we need to study this insertion operation. Yeah. The whole algorithm relies on this operation. Okay, all right. Yeah, so that is the first topic. The second one, insertion operation. 8.2. Let us study insertion operation. The details of this key operation of this algorithm. All right. Okay, yeah. So that's the diagram we did before. Now, so let us look at the typical step using the insertion view on it. Okay, yeah. First, step 1, find the right position. You need to find what is the right position for this new element. Yeah, yeah. Here I should put a sub k here. Okay, I should put a sub k here. Okay, yeah. Anyway, yeah. Step 2, move elements to make array sort. Yeah, because this position you need to move some of the elements to make room for the new element, right? After you put a new element, there is no room. You need to make room for the new element. Yeah, so you need to move some of the elements. Yeah. All right. Yeah, implementation of insertion operation. How to find the correct position for the new element. How to find new position? Yeah, it's pretty easy, right? Yeah, new position. We know, already sorted. How to find? Can you do the comparison in some order, right? Yeah, in some order to do comparison. Yeah. Here, yeah, let us find the position. Yeah, already sorted. Yeah. Second question, how to move elements to make the new array sorted? You need to move some of the elements. Yeah. All right. Yeah. Here you can see when we compare the new element a sub k to the existing elements, the efficiency function, big theta of k. Yeah. Best case, one comparison, right? Best case, yeah, just compare with the last one, and it is greater than the last one. Then the end position is for this new element. So that's the best case, one comparison. The worst case, you need to compare a sub k to all the elements, right? Not k elements. Yeah. The worst case, k. But for others, in between, you can take average. So the whole thing, big theta of k. Overall efficiency, big theta of k. Yeah. What is the average case efficiency? Distributed evenly, right? Yeah. All these cases distributed evenly. But the question is, we want to get a precise expression. Is it k over 2, or k plus 1 over 2? The question I put here, I want to make it precise. K over 2 or k plus 1 over 2. All right? Think about that. Yeah. K over 2 or k plus 1 over 2. All right? Yeah. Okay. Now, shift elements for insertion. Okay. We need to make room for the new element. How do we make the room? Shift elements to the right. Yeah. To the right, we have more locations for the new elements. All right. Yeah. So when we start, the current element is okay from here. So we lift current element k to some temporary location. So this location is empty, right? We store a sub k to a temporary location. Okay? Then this location is empty, vacant. Okay? So we can make the shift. All right. Yeah. All right. But our goal, we need to find somewhere. Okay? We need to put in a target position somewhere. Yeah. So let us do it one by one. First, we lift a sub k to a temporary location. Right? Then we'll compare a sub k with the last one in the current sorted array. If the current element is smaller than this one, we shift it into its next adjacent location. Yeah. Shift to the right, one position to the right. Okay. All right. Then after that we compare a sub k with next element. If it's still less than that one, we shift to its right adjacent location, and so on. Okay? We do this and so on. But we have to stop somewhere. At some point, a sub k greater than a sub I, then it stays here. Yeah. All right, so let's look at this diagram. After the shift, yeah, because these elements, we do the shift. Okay? These elements, we do the shift. Shift operation. Okay? Finally, we get to, we have a vacant place, right? We have like a hotel room, vacant. hotel room, all right? Yeah. Then you compare A sub k with A sub I, it is greater than A sub I. Then we can drop it in that vacant location. That's the whole one insertion operation. One. Yeah. We find the right place, we make the shifts, and we get the whole array sorted. Yeah. So that's this. If you can do this operation for one new element, then you can do it for all the new elements. Okay? So that's simple. All right. Yeah. So you can imagine finally we get this array sorted in this way. So this method we call insertion sort. Yeah. All right. Here, let us count the number of assignments. Yeah. Yeah. Assignments. Yeah. Because when you do the copy, you make the shift. That is the assignment operation. Okay. Variable, value, assignment operation. Yeah. Big theta of k. Big theta of k. Because you have best case, you have worst case. Okay? Average case, approximately, yeah. If we use the asymptotic notation, yeah, that's average case. If you say approximately, you can use about 1/2 of k. But the previous question, when I ask you precisely what is the average case, then you need to tell me k plus 1/2 or k plus 2. Yeah. So if we talk about asymptotic, then it's good enough. You know, even we drop that 1/2, big theta of just k. Yeah. Big theta just k. Yeah. Drop that 1/2. Yeah. All right. So now, then the last topic of part A, insertion sort. After we complete insertion operation, now the whole sorting algorithm is there. So the worst case efficiency, you need to do comparison and assignment, right? Comparison and assignment, worst case, all the way from beginning to end, this many, right? Yeah. Big theta of n squared. Yeah. Worst case efficiency. Best case, look at the best case. Best case, each new element insertion, you just have one operation. Okay? For all of them, you just have n minus 1. So the best case, big theta of n. You can see that is something really nice here. Big theta of n. For the best case, you can get array sorted. Big theta of n. How good it is. Yeah. So this is the biggest property of this algorithm. Biggest property. And this property, special property, not shared by other algorithms. Later you will see no other algorithms have this property. So special. Yeah. Only this algorithm has this property. Okay? Think about that. Okay? All right. Average case, yeah. Average case you need to do the math, but look at the worst case. 1/2 n squared. Average case pretty close to 1/4 n squared. 1/4. 1/2 of the worst case. Okay? Very close to it. Yeah. The leading terms, 1/2. The minor terms, could be different. The minor terms. If we look at the leading term, 1/2. Yeah. But still, big theta of n squared. Big theta of n squared. Okay? All right. Yeah. How to derive it? Yeah. If you really need to do the calculation, then we need to consider each step. The first step, average case. The second step, first insert the first element, average case. Insert second element, average case, and so on. Yeah. Yeah. If that could be sometimes I could ask you that kind of questions. Yeah. If we have a chance, we practice that. Yeah. Average case. All right. Now, conclusion. So for this algorithm, because the best case, look at that best case. Best case, so unique, so good, linear, big theta of n. So we want to take advantage of that. So what is the conclusion? If the given array is almost sorted, yeah. In the real world applications, do we have the situations sometimes we have our data not completely sorted, but almost sorted. Some scattered locations, the data not sorted. Yeah. Using a diagram, line segment, I want to show the situation. Yeah. If in the real world you have a situation like this, the whole array of data not completely sorted, but unordered locations just like this, scattered location. Okay? Yeah. Some, bad spots. Yeah. You need to fix. You need to fix those bad spots. Okay? In that case, insertion sort is the best. That is insertion sort, because you can take advantage of that excellent best case efficiency, big theta of n. If you apply insertion sort, you will get this kind of efficiency. If you apply other, you can use other sorting algorithms in the market. If you use that, the best you can do, big theta of n log n. But this is much better. Yeah. So that's the reason. So this method is the best for this kind of data. This kind of data. Okay. All right. So we complete the insertion sort. Insertion sort. And this insertion sort, so far at this point, we have the basic theory. Basic theory. Yeah, that's the basic theory. But later, I will talk about this insertion sort thinking. Because our thinking based on this algorithm. Later, when we sort certain number of elements, I will refer to this algorithm many times. Yeah. It has some nice property we need to use. Yeah. So we will get to that later. Yeah. All right, so that is the part A of Module 4. Yeah. So we still have close to 20 minutes. Yeah. So I don't want to waste that time. So let us start part B. At least we do some introduction. Okay? Yeah. Yeah, so we should start at the B.1, right? Yeah, B.1, binary search, elimination. All right. First, let us look at our problem number 12. Search an ordered array this time. Yeah. Not unordered. Yeah. This condition is important. Yeah. This condition is important. Ordered array. Don't forget that. Yeah. Why I emphasize that? Yeah. Yeah. It's quite interesting. Yeah, something, I can talk about a little bit. First, let's look at the problem first. Given an ordered array like that, in ascending order already, and a search key V. Question, how to find an index I such that V equals A of I? That's the problem, right? Such an ordered array problem. All right. So here, I emphasize the condition. Before you apply, we're going to use binary search. Before you apply the binary search, the first thing you need to make sure your data is ordered. Why? I repeat this again and again. Because in the real world applications, many people apply the binary search on unordered array. It happens a lot in the real world. So you will get wrong result. Yeah. So that's very important. Okay. Do that check. Yeah. Yeah. All right. The idea. Yeah. Reduce the problem size by ordered data property. Ordered data, that property we need to take advantage of it. That property can help us reduce the problem size quickly, faster, quickly. Yeah. Yeah. But we use elimination method. Elimination method. So this is a good example showing you the power of the elimination method. Yeah. How can we take advantage of ordered data property? Ordered data, you can make prediction well. If you know the data is ordered, then you can make good prediction for the search key location. This is the search key. The search key is in what location in the array? If you have the ordered data property, you can make good prediction. Okay? If unordered data, you cannot make that good prediction. That's the key difference. Right? Yeah. Explore the ordering property. Yeah. So let's look at a typical situation. This is a typical situation. This array ordered, ascending order, new search key V here. Now, when we try to find location somewhere in the array, we have a lot of freedom to choose our comparison, right? Yeah. You can compare V with anyone in the array. You have that freedom. But the question is, which one is the best overall? For you want to get the best overall performance, efficiency. Which one you use it for the first comparison would give you the best worst case efficiency. Yeah. Best worst case efficiency. Okay? Yeah. So let's look at that question. So you can do comparison with any one of them. All right? If you are very lucky, yeah, after one comparison, how many elements can be eliminated? Yeah. Yeah. Let's look at this way using elimination method. After one comparison, you can make good prediction because the data is ordered. For example, you compare with A2. Yeah, think about that. So let us compare with V and A2. If we know V greater than A2, what kind of prediction you can use? If A greater than A2, that means V cannot appear in those elements smaller than A2, right? If V greater than A2, then V cannot appear in this part. If V cannot appear in the part of including A2, right? Yeah, greater than A2, yeah. So let's cover more elements, including A2 elements. V cannot appear. That means all these elements can be eliminated, right? That's our elimination method. All the elements can be eliminated, okay? Now, our goal, we want to eliminate as many elements as possible. Can you find a way such that if we do that comparison, we can make the maximum possible number of elements overall?
Like, would it be doing the middle of the...
Yeah, the one in the middle. One in the middle, okay? Yeah, because sometimes you can eliminate left half, sometimes the right half, right? Yeah, in the middle, left half, right half, they almost have the same size. That's a nice thing, right? No matter it's in the left half or right half, pretty much the same size. It's a balanced way, right? Yeah, it's a balanced way. Yeah. But think about if you compare with this one, okay? Compare, you have two cases, two possibilities. One possibility, the best case, V greater than this, then you have the best case, right? Because you eliminate all the array elements, right? All right, so that's this case. But other cases, then it's not good for you, right? You only eliminate one. You only eliminate one element. Okay? Yeah. Yeah. When V less than A sub n minus 1, you only eliminate the last element. So you have two unbalanced cases, right? Yeah. Extremely good, extremely bad, unbalanced.
But the extremely bad has a higher probability.
Right. Much higher probability than that one. So if you do the weighted average, right, possibility high, you need to multiply that probability as the weight. Weighted average, much higher. Yeah. All right. Here I like to refer to Murphy's law. Because you have a bad case and a good case, Murphy's law tells us it's very likely you will get that bad case, bad one, right? Anything that can go wrong will go wrong. Yeah. You don't like to get into that bad one, right? Yeah, but you know, Murphy's law is something interesting. Yeah, probably based on psychology, right? Yeah, based on psychology, it's very likely you need to deal with it. Yeah, so that's the reason we want to minimize the bad one. We want to make the bad impact as small as possible. How to make the bad impact as small as possible? Balanced. Either two, you can choose either one, equally the same, almost the same. Okay? Then, you know, Murphy's law or not, because either choice, both equal. So no difference for us. Okay? We're happy with either one, right? Yeah. Think about if we choose the element in the middle, either one will make us pretty happy, right? Yeah. But if unbalanced one happy, one suffer, right? One very happy with small possibility, one suffer with big possibility, right? Probability, yeah. All right, so that's the, you know, our strategy, balancing principle here. Yeah. Here, I may like to talk about this balancing principle a little bit. You know. First, what is the principle, right? You can, I think you learn, you heard many different principles. Yeah. This principle, you know, many principles. Yeah. But what are those principles? Yeah. Principles, something nice to follow. If you follow those principles, it's very likely you have good results. You enjoy better results. but you do not have to follow, okay? Because that's just general principle. Okay? Recommended, yeah. You have option to use or not using. Yeah. You have option not using that principle, okay? Because there are so many principles, you cannot use all of them, okay? Yeah, the balancing principle is the one of them. When you have freedom to choose from different options, you have many options here. So, yeah, look at that fake coin problem. Fake coin problem, you have option to choose, fake coin from different piles. When you have freedom to choose from different piles, the best average case efficiency comes from balanced data distribution. Balance the data distribution. That means you should split all the coins in balanced way. Evenly split, right? Evenly split. Okay? Yeah. So that kind of principle, balancing principle, we can use. All right. Compare the one right in the middle. Yeah. Median. Yeah. So that's why we use that element we call a median. Median. So what is the median? Yeah. Still, many students ask me, yeah, although in middle school, the kids learn how to find the median, right? Yeah, the middle school, kids, learn how to find the median. Yeah, but here in this class, still, many students ask me, so what do you mean? What's the meaning? Exact meaning of the median element? Yeah. All right. So let me answer this another time here. The median element. When we talk about median of an array, we imagine that array already, we saw that array in ascending order. Then the element, the one in the middle, is the median. But the question is, yeah, some students ask me another time, if you have even number of elements, the element in the middle, you have two elements in the middle location, right? Yeah. Because equally in the center, right? Left to right, but by symmetry, they are symmetric, right? Those two, symmetric, yeah. So let me explain that situation. Yeah. Yeah, let me use the space here. Yeah, use space here. Suppose this array. Okay? Yeah. When you have odd, no problem, right? The one in the middle, that's the median. No argument. Yeah. But when you have even number of elements, then you have two elements in the middle, but our median, we can only take one of the two. We cannot take both. It must be one of the two and fixed. Okay? Yeah. So what do we mean? In this case, the median, we mean the left median. The one in the left. We call the left median. Left median is the default median. Default median. All right? That means if it's not specified, if people do not say left median or right median, people just say median, then we talk about the left median. Yeah. Not right median. Okay? Left median. Default. Yeah. Yeah. All right. Yeah. So that's the meaning. All right, so let me stop here. Yeah. Here because we treat this as introduction of our binary search. Yeah. We just describe the typical situation. Yeah. So next time, Wednesday's class, let us do the solution.